Okay, it's 6 o'clock. Welcome all to our IEEE Vehicle Technology Society Chicago Chapter webinar. So thank you all for coming here tonight, and hope that you're all continuing to stay healthy and safe. So this is our August webinar, and tonight we have Professor Chi Ju, who will be our speaker, and he will be talking about knowing the unknowns, addressing disturbances and uncertainties in connected and autonomous vehicles. So my name is Alvin Chin. I am the chair of the IEEE VTS Chicago, and I'm also the senior researcher at BMW Technology Corporation in Chicago. With us for our webinar this evening, we also have other groups as well who are joining. So I'd like to thank those particular groups. In particular, I'd like to thank the members of the Mid-America Club ITCONNECT group that are here this evening. I also like to thank the Society of Society of Automotive Engineers, SAE Chicago section as well, for having their members join this evening. Also, we have members from our IEEE Computer Society Chicago chapter as well this evening. And this webinar would not be possible without the support of Northwestern University Transportation Center. In particular, I'd like to thank Hani Mamasani and Brett Johnson for their help in actually being able to have and suggest Professor Chi Ju to be our speaker for our IEEE VTS Chicago event. So I'd like to thank all those individuals for helping us for this evening. Okay, so a little bit about the VTS Chicago chapter. So you can find our website at IEEE Chicago. Oops, sorry, just go back. Yeah, so you can find us at IEEEchicago.org/VT, and we are the Chicago chapter of the VTS Society, vtsociety.org. Like I said, I am the chair of the VTS Chicago chapter. Our vice chair is Kevin Studenberg from Argonne National Laboratory, and we also have our IEEE Young Professionals VTS student chair, Drew Chen from IIT. Our mission for VTS Chicago is to create a community of academics and professionals talking about technology and engineering in the vehicle to create connected vehicles and autonomous vehicles. And we usually have our meetings, usually physically, at least 3 times a year, but obviously afterwards, after March or so, we've had all our meetings online, and at least now for the foreseeable future until we are able to go back and have our physical meetings. If we were to do this physically, it would be held in our in the BMW technology office where I work at in Chicago. We've also held it in other offices like Argonne National Laboratory as well. The topics that we discuss about are vehicle ad-hoc networks, 5G, autonomous and connected and electric vehicles, vehicular network, cloud, connected vehicle platform, smart cities, power and charging. And you can find us here on our Facebook, LinkedIn, and Twitter on social media. And if you are posting on social media, please tag your post with IEEE #IEEE VTS Chicago. Okay, so I will now give it to VJ to, 1 second, to give a few words on the Mid-America Club. So, okay, VJ, go ahead.
Hi, Calvin. Can you hear me, please?
Yes, I can hear you. We can hear you.
Okay, great. Yeah. Thank you for the introduction, Alvin. My name is Vijay Kunkimala. I'm the chair and the founder of the Mid-America ITCONNECT, and we started this ITCONNECT club about 3 to 4 years ago, and we do cutting-edge technology presentations on different topics. And today, we're going to talk about, as Alvin mentioned, the disturbances and uncertainties in connected and autonomous vehicles. So again, this is one of the very exclusive clubs in Chicago, which is in the Aon Center on the 80th floor. So if you have not visited the club, you should come and visit the club, and it's a great club. And you should come to our future events as well. Thank you, Alvin. You can take over now.
Okay, thanks. Yes, so just to add to VJ on this, we actually had our first VTS Chicago event was actually at the Mid-America Club in January. So hopefully we can be able to, when we are able to resume, also go back to the 80th floor as well. Okay, thank you, VJ, for that. Our next group that we're here tonight is the IEEE Computer Society Chicago chapter. So this is the Chicago chapter on IEEE Computer Society. This chapter talks about topics dealing with software, hardware, computing, AI, big data, cloud computing. We've done stuff with cybersecurity. So we've worked together with a organization called FutureCon that has cybersecurity conferences. So we actually participated in their actual conference that they had in Chicago, right in actually early in March before the lockdown. So we also worked together with them. For this chapter, I'm also the chair of IEEE Computer Society Chicago, and our vice chair is Gina Martinez, who's also in the meeting this evening. And if you want to know more information, here is the links to our web, to our Facebook. We have a Twitter handle as well as LinkedIn. Okay, so now I'm going to turn it to Mike Belling. So I'm going to have him, hold on a second. Let me find Mike here. To go ahead and talk about SAE Chicago. So here we go. Okay, Mike, you should be able to talk.
Hey guys, I'm Mike Bailing, the vice chair. I just want to say hi from me and Tim from SAE Chicago, our current president. Welcome and thanks for hosting, Alvin. We're just a society of automotive engineers, so kind of all things automotive related. We've paired up with these guys before, IEEE, on some other automotive events as well, and we've had our own. We're looking to have some more this fall, as well as an auto show coming up, so a virtual auto show. And if you do need a PDH, that's available. Just email us at our MS013 email, or kind of shoot me or Tim or any of the officers a link. So looking forward to this event, and as well as this is open kind of to anyone. If you want to be part of that virtual car show, just kind of get in contact with us at that MS013 email, or you can find our contact information on our website as well. So thanks everyone.
Okay, thank you, Mike from SAE Chicago. Okay, so VTS Society, we have a conference. We actually had 2 conferences a year, spring and fall. And for this year, because of the pandemic, it's all being held virtual. So originally, the fall conference from October 4th to 7th would have been held actually in Victoria, British Columbia, and Canada, but unfortunately, it is now being held virtual. Here is the link to the conference. So all the talks will be recorded, but you can register for a discounted price if you want to attend online the conference. Okay, and also as well, we also have the, oh, sorry, just go back here, I went too fast. So also, there's also the VTC conference as well that we have, like I said, for spring and fall. So there is a spring one happening next year, 2021, is planned to be in Helsinki, Finland, in April 25th to 28th, if everything is okay and travel is allowed. The reason why I put this here is that because for those particular people that want to submit a paper to the VTC conference, the deadline is in about 1 month. So the deadline is September the 28th. So if you have any ideas or you have any particular research or work that you want to submit to the conference, you can do so. You can find more information in this link. And yes, if you want to become an IEEE VTS member, there are very many benefits to that. So you have a free access to our resource center of lectures, keynotes from previous conferences, panel presentations from VTS events. You have access to our VTS Mobile World newsletter. And actually, just recently for the month of June, VTS Chicago was actually named the chapter of the month. So thank you to VTS for that distinguished honor. You also have free printed copies of the Vehicle Technology magazine. We have also other publications too and conference proceedings. If you become an IEEE VTS member, then you get discounts for VTS sponsored conferences like the one in the fall and spring. And here's the link if you want to know more information about membership. If you are a VTS member, thank you for your support. I'm actually running for the VTS Board of Governors. So shameless plug, if you receive the voting ballot from IEEE VTS, please vote for me for IEEE VTS Board of Governors. Okay, so of course, enough of me talking. We have our speaker this evening, who is Professor Chiju from ECE and in Northwestern University. Just a little bit about himself. He got his PhD from UC Berkeley and Bachelor of Engineering from Tsinghua University in Beijing, China. He specializes in cyber physical systems, IoT, cyber physical security, safe and machine learning for cyber physical systems. He's won Best Paper Awards at DAC 2006, DAC 2007, and so forth, that you can see there. He's also works with the academia community, working in conferences. So he's a conference chair of IEEE TCCPS, associate editor of IEEE TCAD, and other events too as well. Okay, so just before we start, just to let everybody know that this webinar is being recorded. And after this webinar, all of you that have registered will receive an email to the link to the recording. And as well, we will provide the slides afterwards. So you can have a copy as well. And we will have questions and answers after Professor Ju finishes talking. So as you can see in the Zoom UI, you will see a Q&A kind of a button or an icon there. You can write your question in the Q&A. We will collect those questions, and then Kevin Sudenberg, our Vice Chair of VTS Chicago, will take over and will moderate those questions. Okay, so without further ado, I'm going to turn it over to Professor Chiju. So I'm going to stop sharing. And Professor Ju, you should be able to share your screen.
All right, let's see. Can you see the slides now?
Yes.
All right. Great. So thanks, Elvin, for the invitation and the kind introduction. It's my great pleasure to be here to virtually and to share some of our recent work. This is actually the very first time I'm giving this particular talk, so some of the slides actually are very new. So please excuse me if there are places that are not quite smooth, but hopefully I'll try to make it interesting. So our group at Northwestern, we work on these automation techniques for intelligent assistance. So our goal is to create automated and rigorous tools and methods for the design, validation, offline update, and runtime adaptations of intelligent systems. So this could include connecting autonomous vehicles. We also have been working on energy efficient buildings, multi-agent robotic systems, and a few other applications as well. So today's talk will be focusing on connected autonomous vehicles, and excuse me. And as we know, autonomous vehicles in recent years have really made a significant advancement. And if we consider autonomous vehicle, it interacts very closely with the physical environment, and includes a variety of sensing, perception, planning, control algorithms, which will sense the environment and percept what's the current situation, and then automatically make decisions for navigation, for planning, for control. Now, those types of algorithms, right, they will be implemented on embedded software hardware platform. And during this whole design of the algorithm and the implementation on the software hardware platform, there are a variety of challenges. For instance, we have to consider now the highly dynamic environment, the complexity of the functional layer in terms of the scale and the features or the sheer volume of the software content has been increasing drastically. And there's increasing usage of machine learning techniques, which will be one of the focus today. Now, on the other side, the architectural platform, the complexity has been increasing as well. There's an increasing number of ECUs being used. Each ECU has become more advanced with multi-core CPUs and GPUs that are being applied. And there's this general sort of movement right from the traditional, more isolated, federated architecture now to a highly integrated architecture where you will have different functionality, sharing, sensors, sharing, communication platform, which lead to more contention as well. So this all will make the design more challenging. On the other side, you have very stringent requirements on those systems in terms of the safety, in terms of the reliability, performance, cost, and a lot of those requirements are also highly sort of timing related. You have to make sure not only the computation results are right, but also they are being done within very stringent deadlines. So we'll touch upon some of those aspects today as well. Now, in particular, I want to talk about the various sort of the uncertainties and the disturbances in connected autonomous vehicles. So what are those? If we consider autonomous vehicle, it operates in a highly dynamic and uncertain environment, which then naturally brings a lot of uncertainties to the input. And then at the sensors, while the sensors are sensing this environment, there will be added noise as well. Now, typically, the sensing input nowadays are being processed by deep neural networks, and many of which we still don't have full understanding of their operation, and which will lead to the uncertainty as the perception output, which of course would be the input for the next stage of planning and control and decision making. Now, for planning and control, there's a traditional, more model-based approach where you build a detailed physical model and then apply control based on those. And their inherent inaccuracy come with those models. But the more challenging is nowadays there's also increasing interest of applying neural networks to planning and control as well. And that brings a lot of challenges and uncertainties how those neural network-based controllers may work. This is something we'll talk about today as well. And then when you apply actuation, there might be actuation noise. And then when you implement those sensing, perception, planning, control algorithms in software and hardware on the embedded platform, during the execution of those software and hardware, there might be uncertainties, disturbances to them as well. For instance, you may have prolonged execution that may violate your timing constraints. You may have software errors, right, that come from hardware faults or environment disturbance. You may have the operation be disturbed even by malicious attacks, right? And those also further complicates the situation. And then if we consider the connected aspect where the vehicles may communicate with other vehicles or surrounding infrastructures, right, to improve efficiency or safety. Now, those communications go through the vehicular network. They could be disturbed as well. There could be jamming, flooding attacks, or just typical noise in the wireless communication. And so there is a variety of different uncertainty and disturbance. Today, we will focus on a few of them on the perception and planning control side, especially focusing on when we use neural networks. Then we will talk briefly on the software hardware execution uncertainties and the communication disturbance as well. So given the time, I will try to just give the high-level ideas of each part and won't go too much into the technical details. If you're interested, you're of course welcome to follow up and discuss in details. So let's start with the neural networks. Now, if we think about the neural networks, which has been increasingly applied in vehicles and a variety of other autonomous systems, right? So a typical pipeline for this types of autonomous systems, especially vision-based autonomous systems like the vehicles, where you have your raw data, this is imaging data comes in, right? Then you go through the sensing and the perception stage, and then the understanding of the environment, which will then be sent to the planning and control module to make control decisions, right? And as I mentioned, neural networks could be applied for both the perception part and also planning and control part. Now, we have done some work on each of those aspects. On the sensing and the perception part, we have recently proposed an approach to conduct output range analysis, which mostly focus on address adversarial attacks. And then on planning control part, we have done some work on so-called reachability analysis. This is try to reason about the safety of applying neural networks in control system. And I'll briefly talk about both of them. Now, let's start on the sensing side. Excuse me. So when we apply neural networks on sensing the perception, one of the challenges is so-called adversarial attacks. And mathematically, it also sort of similar to if you have sort of environment interference or noise in your input as well. But the adversarial attack example, there are instances that's more intentional, where you will, the attackers will apply intentional perturbations on the input image, right? And those perturbations, in many cases, they are quite small. And if you look at the examples here, this some of the very classic images, you can see the right, the left column is the original image, and then you apply a noise, which is the middle column, and then when the right column is what it seems to you, which to human eye looks almost the same, right? But to the neural networks that try to perceive this image, they will see differently. They will actually all classify all those as ostrich, right? So which obviously is not what you want. Now, so mathematically, if we want to consider this problem, what we're essentially looking at is when we apply a certain perturbation to your input, how much will that affect your output of your neural networks, right? And essentially, this is related to what we call output range analysis problem, giving a compact input set X, right? What can we calculate? What would be the output range? What would be, in many cases, a tight over approximation of your output range? like what's showing here. What we want to have is a relatively accurate estimation of this output range, so we know when you give us a certain disturbance, right, how the neural network will react. Now, there are two main ideas in our work in this area. One is what we call divide. So the main idea here is in your neural networks, you have a lot of neurons, and on the neurons, you have so-called activation functions. And in many cases, those are nonlinear activation functions. Now, to derive the input-output relation, right, of a neural network, you would want to, for each of those neurons with those nonlinear relations, you want to derive this input-output relation as well. Now, traditionally, in conventional approach, there are basic so-called interval relaxation methods. Basically, if you give me an interval of x, as you can see here in the figure on top, if you give me an interval of x, I can estimate the output interval y, right? And the approximation essentially views every point, right, in this rectangle as sort of valid. And the approach that can help you do this, there's interval bounded propagation, IBP, or symbolic interval propagation, SIP. And those different methods will help you to derive what would such sort of a rectangle sort of approximation is. But obviously, this is very sort of coarse approximation, right? So if you give input x, I give you this maximum possible output bound of y, then after many layers of propagation, the eventual output range of your neural network could be quite large, right? So you wouldn't have a very accurate over approximation. So that motivates our work. So instead of using this very coarse interval relaxation, we further use a polytope, right, to approximate this nonlinear function. As you can see here, we can, based on left and right derivatives, and to have this linear polytope relaxation or LP relaxation for this region. And then, if you want to further increase the approximation accuracy, what you can do is actually you can divide this input interval into multiple segments. So this is where the divide comes from, right? The more segments you have, the more accurate the approximation you are. So this is a very straightforward idea. Now, consider you have a neural network where you could have tens of thousands or even more neurons, right? So if you apply a very sort of accurate multi-polytope based relaxation for every such neuron, the complexity will be very high, and it's very difficult to handle those. So what we do is, instead of doing that, we have an iterative approach where we'll pick some of those neurons that we deem as more important and more impactful, and we'll gradually refine them. When we refine them, in principle, when you calculate, for instance, this red neuron, right? Ignore the equations. We won't go into the mathematical details. When we try to refine this red neuron, right, try to make the approximation more accurate, in principle, we should have actually calculate its output range for this neuron by looking into all those neurons before it, right? The cone sort of before this red neuron, and solve our optimization problem and derive the output interval. That will be too complex. Instead, we only look into a few layers before this red neuron. And so this is what we call slide. So you can imagine there's a sliding window. When you pick a neuron to refine, you only look into the sliding window, sort of a limited sliding window before you. And this we can effectively help us to reduce complexity. And we have also proved the soundness of this approach. All right, and so this is sort of like the overall flow of our approach, where it's a combination of, for each neuron, we have this division of the input space to refine this over approximation, and then we select iteratively select the number of neurons to keep refine them, And every time when we refine them, we use this sliding window-based refinement approach. So without going into too detailed into the algorithm, let's just quickly look at the results. So this is something we have done very recently, and we compared with the state-of-art approach. There's a tool called NV, and as you can see here, we have achieved quite a significant improvement in terms of output range estimation over NV, anywhere between a bit more than 10% to more than 90%. And also, our approach is a lot more, as I said, more scalable. So when we increase the size of the neural networks, you can see the computation time of our algorithm increase relatively slowly, right, all the way from around 1,000 seconds to 3,000 seconds also, while you can see the execution time, computation time for NV increase quite drastically. In fact, what's not shown here is, as you can see here, we have tested a small set of neural networks in MNIST. We have also tested the larger ones for CIFAR. For those ones, our results in the paper, but for NV, they were not able to got the result for many of the CIFAR neural networks because of the longer runtime. All right, so this was the work we did on the subtle sensing and the perception part. Now let's take a look at the planning and control, right, where increasingly there has been interest of using neural networks to do it, to apply decision making in a way. And for instance, there's attempt, right, using reinforcement learning. Sometimes we call it deep reinforcement learning, even though the neural networks are typically not that large. And use reinforcement learning to learn to play games. There's imitation learning, right, where you try to mimic the behavior of some experts, right? So the difference here is reinforcement learning, you have a reward function where you try to optimize, while imitation learning, you try to minimize the difference between you and the expert. And there are also attempts of trying to develop neural networks that to approximate the behavior of non-model-based control, like model predictive control. So those are different types of sort of usage of neural networks in control and in decision-making in general. Now, when we consider using neural networks in control, one of the key aspects is the safety, right? So our consideration of the safety for neural network control system on NNCS is what we call reachability. This is sort of one definition of safety. What it means here is assuming we start from initial state, right? And we have a target state. And the question is, when we go from initial state to the target state, will you be able to reach that target state without hitting some of the unsafe states showing here this rectangle? This is the state that you try to avoid. And the problem of reachability analysis is basically to say whether we can go from initial set to the target set without hitting those unsafe states. Now for this problem, there has been a lot of work, that's traditional work for model-based system, how to do reachability analysis. For neural networks, right, if we want to reason about this problem, the key comes back to how do you reason about the behavior of a neural network-based controller. Can you approximate it, right? And a neural network controller given to you is a highly complex system with a lot of neurons. Is there a way to analyze it that is mathematically sound and efficient? Now, our idea here is to use a polynomial, so-called bursting polynomials, to approximate the neural network controller. And essentially, we try to find bursting polynomial to approximate the behavior of the entire neural network. So the entire neural network can be approximated by one bursting polynomial. And this approach, the one advantage is it works for any Lipschitz continuous neural network. So regardless of your activation function, whether it's ReLU or tangential sigmoid or combination of them, this approach applies. And the idea, of course, is try to make your bursting polynomial approximation as accurate as possible, right? So if you here have this black line as the neural network output, right? And the idea is try to make this green line as close to it as possible. Now, so we have proposed approach to do this. Given the time, I won't go into details how we do that, but let's take a look at the results. So here it shows the result comparison actually between our approach and a couple of other state-of-the-art approach tools. One is called VeriSeq, one is called Sherlock. VeriSeq is from University of Pennsylvania. Sherlock is from University of Colorado Boulder. And if we take a look at it here, the red curves, those are the simulation results. You can view this as the ground truth. And the green curves, we call it curves, actually it's this trajectory is the concatenation of a bunch of rectangles. This is estimated sort of range of our tool. And the green ones, those are the estimated sort of trajectory from our tool. This is the over approximation, as you can see. And the green ones, the gray ones are the result from VeriSeq. So as you can see, the our tool can give a much more accurate approximation of the neural network behavior. The eventual blue square here, this is the target range, right? And so in most of the cases, we can verify that we can indeed reach the target range without with safety guarantees, except for one. The second, except for the first one, where you can see our green estimation actually exceeds the target blue box. What that means is we cannot give you a definitive answer whether this is safe or not. But in vast majority of the cases, our tool were able to do that and outperform other tools. And one of the biggest challenge for our tool, and also for many of the other tools in this area, is scalability. So basically, what we're trying to do, right, is to approximate a highly complex neural networks, and then we have to verify whether the system will be safe over many steps of the system, right? So this is a computationally very expensive process. So to speed up this, one of the key steps and very time-consuming step in our work is the error estimation of the neural network approximation, of the Berkeley polynomial approximation. And to speed up that, we proposed the approach to the approximation is based on, the error estimation is based on sampling technique. So we use the technique to partition the sampling space and then to parallel this execution on GPUs to speed things up. So that's one extension that we recently published. And then there's another extension we did that's quite interesting. So what we observed was in our work, our approach and also another tool, VeriSeq, both tools, the efficiency highly depend on the value of the Lipschitz constant. Now, as you can see here, from left to right, the Lipschitz constant of the neural network is getting larger. And the first line is our result for our tool called ReachNN. The second line is for VeriSeq. The third line is for Sherlock. As you can see here for our tool, right, when the Lipschitz constant is getting larger, our estimation becomes increasingly inaccurate. And not only that, you can see that in the last case, right, we actually would not be able to continue to compute after certain steps, because after that you can see the estimation already hits the unsafe boundary, so we don't know whether this will be safe or not already. And further, you can see the runtime increase quite a bit. For VeriSeq, there's similar issue. When the Lipschitz constant gets larger, we wouldn't be able to find the solution because of the approximation gets longer. Approximation error gets larger. However, for VeriSeq, they don't suffer from the computation time. And Sherlock is not affected too much by Lipschitz constant value because of the way their approach works. So what this tells us is if we are able to reduce the Lipschitz constant of a neural network, we will actually make the neural network easier to verify. So this is a direction that we feel very passionate about. So when we design neural networks nowadays, the main objective we think about is the performance of the neural network, right? And but to really enable the application of the neural network, you really have to verify their safety and other properties. So it would be beneficial if when we design the neural networks, we put verifiability in mind, right? Try to design a neural network that's easier to verify. So what we propose here is a knowledge distillation approach. Basically saying, if you give me a neural network that you have already designed, and we will try to retrain another neural network that has a very similar performance to what the original one is, but has much smaller Lipschitz constant, so it's easier to verify. Right? So now I have two objectives in this retraining process. It's called knowledge distillation because I'm trying to learn the knowledge from this original neural network, try to learn a new one, but the new one will be easier to verify. Now, when in this retraining process, we have basically two objectives. One is to reduce the regression error. Basically, this is the error between the neural network and the original network, right? You still want your neural network to be as close to the original one as possible. And then the other one is you try to reduce the Lipschitz constant. And the way we do that is we have a dual objective gradient descent approach where we sort of will have weighted sum of the two gradients, one measuring regression error, one measuring the Lipschitz constant. And by doing this, we are able to find, as you can see here in the result, we will be able to find train a new neural network that has as good performance, but much easier to verify. As you can see here, from right to left, sorry about the order, from right to left, the Lipschitz constant for our tool is getting smaller and smaller, and then you eventually will be able to verify that the design of the neural network actually can successfully reach your target without hitting, without hitting either of those obstacles, so being safe. All right, to quickly recap, on neural networks, we try to address the uncertainty, both for the perception neural networks and also for neural networks that are being used in control and decision making. Now let's briefly go through the, given the time, let's briefly go through the other two aspects. One is the execution uncertainties, right? Once you have implemented those algorithms in software and hardware, what's the uncertainties that could happen in the operation and how we may address them. Now, a variety of uncertainties or disturbances could happen in computation, communication, or storage of those software hardware implementation. For instance, you could have timing violations, right? Things take too long to complete. You could have transient errors. You could have attacks from malicious attackers. So a lot of those uncertainties or disturbance, the effect of that is you're missing the deadlines, right, of your operation. So for instance, if you think about a vehicle, right, you have a lot of those so-called end-to-end latency deadline. For instance, from the moment you sense certain event to the moment you want to apply control, right, there would be an end-to-end latency deadline. And you don't want to miss that. Traditionally, there are sort of a couple of different ways to set deadlines. One is to set so-called hard deadlines. And this is the prevalent ways to dealing it in automotive industry, right? So hard deadlines are the deadlines cannot be violated in any circumstance. And this types of definition often requires very complicated and in many cases over conservative worst case timing analysis. And they may lead to, in many cases, lead to infeasible designs or over provisioning of your resource. And it's increasingly hard to do it because of complexity of the functional and architecture. On the other hand, you may set so-called soft deadlines. So those deadlines can be validated at any time. And it gives you a lot of flexibility in design, but the problem is it cannot provide any deterministic guarantees on system properties. And for safety critical systems like vehicles, this is not ideal. So what we have been proposing the last couple of years also is a new paradigm called weakly hard paradigm. So this is motivated by many of the system functions, control functions, sensing functions. They actually can tolerate certain degree of deadline misses, as long as those misses are bounded and controlled. And a common type of weakly hard constraint is so-called MK constraints, which specifies among any k consecutive activations, you can have at most m deadline misses. Right? And this is a constraint that's more flexible than hard real-time constraints, but on the other side, provide more deterministic guarantees than soft real-time. In fact, mathematically, if you think about it, right, it is more general than both of them. MK, when M is 0, is actually hard constraints. When M is K, is become soft deadlines, right? So how can we leverage this? So basically what we can do is, there are two ways. One is if you have a system that is already designed with limited resource and it's very difficult to make changes, right, because of the rigid hard real-time constraints, what you can do is you can study some of those functions and find whether they can actually afford some deadline misses and try to extract those slack. What we found is for many of those functions, even if you allow a little bit of deadline miss, say 1 out of 10, that already gives you a significant amount of scheduling flexibility, where then you will be able to use to make changes to your system, to add a new functionality or making changes to existing ones. So basically enable retrofitting of your system. And another possible usage of this is you can imagine you have a system that operates in a highly dynamic environment, right, with disturbance and all that. And you can have a runtime monitor to monitor the possible errors or faults that happens. Now, in a hard real-time system, when you see an error, you may already have to go to a failure mode, right, because it's considered a violation of the safety. But in weakly hard system, if you know certain functions actually can afford some deadline misses, then what you can do is you can actually let it keep running, but as long as you keep in mind, right, as long as it doesn't violate the weakly hard constraint, you don't have to immediately go to failure. So the key of applying weakly hard paradigm is, we got this question all the time, is to make sure that the allowed deadline misses, right, will actually still guarantee the system satisfying its different types of requirements on the safety, on the robustness, etc. This is the key because you don't want to, by allowing deadline misses, actually lead the safety system to unsafe state. And then on the other side, so this is what we have to do as a functional layer to reason about functional and extra functional properties based on deadline, given deadline misses. And then at the software layer, we have to reason about whether the system is still schedulable on the weakly hard constraints when you add new changes to the system, right? Try to leverage those slacks. And then at the operating system layer, we have to have new scheduling policies to leverage and support weakly hard paradigm. So I have done a series of work across all those layers. It's really critical to take a cross-layer approach for this problem. And very importantly is we have to figure out how do we set weakly hard constraints on functions to drive the system design, right? And because at the end of the day, when you allow deadline misses, there's a trade-off between the performance and the additional flexibility you get on your design. And when we try to set those weakly hard constraints on functions, we have to consider different objectives in our system across functional layer and the software hardware layer as well. So I think given the time we have, I will skip the details of those. I want to briefly mention one of the work we did on the weakly hard system. This is on trying to leverage weakly hard constraint to improve vehicle safety, vehicle security. So we, in recent years, has been increasing attention on the security challenges for vehicles because of the variety of newer interfaces being developed for vehicle communication to communicate with outside. and also because of the drastic increase of the software content now in vehicles. So there has been demonstrated a variety of potential malicious attacks can be applied to vehicles. While the traditional in-vehicle architecture of a vehicle was not really designed with security in mind. For instance, the CAN bus, controller area network bus, there's no sort of built-in security mechanism, right? So one of the possible issues of that is if the malicious attacker can compromise any one of those ECUs, right? Even some seemingly unimportant functions like MP3 playing, then they can send messages over the CAN bus and try to compromise the more safety critical components like engine, transmission, brake components. And to prevent that, a variety of techniques have been proposed. For instance, lightweight authentication methods, using message authentication bits, or adding security monitoring tasks, right? But the challenges for adding all those is automotive electronic system is already very heavily utilized. It's often very difficult to add new functionality into it without violating timing constraints or resource constraints. And even if you are able to add it, you have to be very careful of analyzing its timing, and it's a very challenging task. So what we propose in this work is essentially to leverage the VKH constraint to formally derive for some of the functions how much they can sustain the deadline misses, and try to leverage the slack you obtain to add the security monitoring tasks. So that's the work we did in this area. All right, so lastly, I want to talk about on the connectivity aspect, connected vehicles. So for connected vehicles, recently there has been lots of interest. This is by leveraging Vehicular Ad-Hoc network. The vehicles can communicate with each other and with the infrastructure. They may share information on their speed, location, acceleration, etc., to improve the safety of the vehicles and the efficiency of the transportation network. And one of the examples we have been looking at is so-called autonomous intersections, where the vehicles, there are different types of them. For instance, there are centralized autonomous intersections, where the vehicles could send a request to an intersection manager, then the intersection manager would essentially be scheduling, and those requests decide who can go first, then the vehicle can proceed, right? And in ideal world, these types of autonomous intersection can function well, improve the efficiency of the intersection compared to the typical traffic lights. However,
oh, hi. Yes. Hi. Could you finish in about 1 minute so we have time for people to ask quick Q&A, if you don't mind?
Sure. Okay.
Thank you.
Okay.
Yeah.
I'll wrap up then. Okay. Then in this case, a lot of the previous work they were done based on the assumption that communication is perfect, and when the design autonomous intersection, they actually divide the intersection into grade, and then as long as the two vehicles will not be in the same grade at the same time, they consider that as safe. Right? Now, this is obviously a very aggressive approach. In reality, a lot of communication for vehicle-to-vehicle communication, they do have disturbance. They could have long delays when you have a large number of vehicles, and the delay can get even longer with under security attacks, jamming or flooding attacks. So what we did here was we proposed what we call delay-tolerant protocol, where we explicitly consider the possible communication delays or packet drops in vehicle to infrastructure communication. And we build our protocol based on that. And then we formally verify the properties of this protocol and guarantees safety, deadlock free, and shows that the performance of such a design outperforms the more traditional, conventional traffic lights, and also outperforms so-called smart traffic light, which basically intelligently adjust the green and red period of the traffic lights. And so these types of work we thought ultimately could be very helpful to help the design decide, right? When we try to develop certain self-driving or V2X vehicle to infrastructure or vehicle-to-vehicle applications, what are the things, what are the factors we have to guarantee their software hardware design to make sure those applications actually are safe and robust. So that's the idea. All right, to summarize, we have looked into a few different uncertainties from the usage of neural networks in perception and planning and control, and to the software hardware execution and to V2X communication. A lot of this discussion are stayed at a very high level, but if you are interested, as I mentioned, we can follow up on those topics. And I just want to quickly acknowledge my students, postdocs, and collaborators, sponsors on those work. And at the end, there's relevant publications, and I understand this slide will be shared, so we can check those out. All right, thank you very much. It's rushed a little bit, but if you have any questions, I'm very happy to answer them.
Okay, great. Thank you, Professor Zhu. So we have about several minutes, so I'll hand it over to Kevin to do the Q&A. And what I'll do is that for those that are still here, I'm going to launch a poll so to give us some feedback for our future seminars. Okay, so go ahead, Kevin.
Sure. First off, thank you very much for the presentation. That was very interesting. I would like to mention to any of the attendees that if you do have any questions, feel free to go through and post those in the question and answer session right now, and we'll try and get through as many of them as we possibly can. One question that was posted a while ago was, is there any work being done to bridge this theory, which I believe the theory that was mentioned was on it was on the Bernstein polynomial approximation, and they were wondering if there was any work being done to bridge this theory in industry. And anytime I'm engaged with a recruiter or a hiring manager, they're sticklers for software programs like Microsoft Azure or Apache technologies like Spark or Kafka and other programming languages, and they had said that they're rarely asked only once if they knew of that theory. So
that's a good question. I think that, and I think both people from academia and industry can view this. For a lot of the work I'm talking about today, I think they are still at the early stage, right? The application of neural networks in perception network has been more mature. The application of neural networks in control, in decision making in general, has really just got started, and the safety challenges for that is something still, I would say, very much an open challenge, right? And but I do feel it's very important while we are doing this to have a close contact and even collaboration with industry on this to figure out the challenges and to bridge those research. We have been in discussion with a couple of companies on those, and showed interest in looking into those problems. I think for the second part of the questions or comment, right? I think on the hiring manager side, the things you mentioned like Spark and all that, those are very popular tools, right? And relate to machine learning and some of the software assistance. But for instance, I mean, a lot of those work, they come from academic research as well, right? So, so I think those things take time.
thank you. Yes, if there and no other questions, please post them in the question and answer session. I do have a few as well. So have you looked into, I know you kind of dabbled a little bit into automotive or the cybersecurity basically of the communication networks that are on vehicles. Have you looked into some of the advanced automotive networks such as like GM's Global B that will be coming online or kind of has within the last, I think, year in the Cadillac C5 and the new Corvette where there is a bit more security that's kind of built into those systems off that, and how do you see that kind of applying with what you had mentioned?
Right. So the work we started looking at automotive, especially for instance the in-vehicle security, right? So there are two things: one is in-vehicle security, one is the vehicle-to-vehicle communication security. For in-vehicle security, we started looking at it around 2013, 2014. Some of the vulnerabilities were exposed around 2010, 2011. Since then, there has been a lot of work actually in industry looking into this as well. while we are doing our work, we started looking, for instance, at CAN, which is existing, is a prevalent bus protocol, has been in vehicles for many, many years. Right? And we found that for CAN, it's very difficult to apply some of those sub-secret techniques. But we also looked into more sort of emerging protocols, for instance, Ethernet-based ones, TT Ethernet, etc., right? And TSN more recently. Now, for those more emerging protocols, they have much higher bandwidth, and it's easier to add into some of the cybersecurity measurements. But what we found is you still have to be very careful in your timing analysis of the potential overhead those techniques brings, because for vehicles it's such a safety critical and time critical system, you have to really have a rigorous analysis to show that the timing constraints are being satisfied. And even for those faster bus that's needed, we observed that the timing can be affected quite a bit by those cybersecurity measurements. Right? And but what I touched upon in the talk was only on the in-vehicle communication network. There are other aspects as well. There's increasing discussion of, for instance, put security measurement on the gateways, on the interface, etc. So industry has done a lot of work on that aspect. So I think, yeah, we look into to summarize, we're looking into some of those aspects, some of the newer protocols, and for the vehicle-to-vehicle communication security challenges, we were mostly focusing on DSRC before, but we recently started looking into 5G as well.
Thank you. All right. Let's see. I think there was a little bit of a follow-up on the prior question where there was what was stated is what is frustrating is a connection between theory versus what is asked for in industry, and then is there any work being done to ensure that that there is a bridge in between the theory into the industry? I think was what they were trying to really last question.
Right. I think what we found very effective. So first of all, I think I share this view. I think it would be great, I think, for a lot of those problems to have a even closer academic and academia industry collaboration. In our group, we have been working closely with some of the industry groups. So for instance, the vehicle communication work was in collaboration with Toyota, and the earlier work on a lot of software work, which I didn't talk about, was with General Motors, and we found those collaboration very helpful. And the knowledge transfer of some of our findings to industry, sometimes that could be challenging. And if the students eventually go to industry, I think that's a very effective way of spreading those knowledge. On the other side, from industry, their feedbacks and all that could be very helpful in our community. So I'm very involved in embedded system and design automation community. Some of the major automotive companies, they have researchers and engineers very much involved in those, and have a lot of involvement, for instance, in design automation community from Bosch, from GM, from Toyota, so and many other companies. So those has been very helpful in my view. But this is, I mean, this is a very big challenge. I think it really takes both sides try to work more closer together. Now, what's interesting now with this all new sort of trend with neural networks, right? I think we are seeing more interest to work closer together on both sides because this is something very new, right? And really, there's so many unknowns, and really it'd be helpful for both sides to work together to address.
Thank you. All right.
Okay. Thank you, Kevin, for that. So I think for the interest of time, we are about 4 minutes over 7 o'clock. So conscious of everybody's time. So we'll wrap it up. Thank you very much, Professor Chiju, for giving the talk this evening. And like I said earlier, this talk is recorded, and we will have slides available, so you will receive that in your email after this webinar. And stay in touch. We will have our future IEEE VTS Chicago webinars for the remainder of this year, so please be on lookout for email, and also to check our social media sites as well. Okay, and so with that, again, I'd like to thank, on behalf of IEEE VTS Chicago, I'd like to thank you all for attending this evening, and stay healthy and stay safe, and we'll see you for our next webinar. So have a good night.
Thank you. Good night.
Thank you.